Hello, I'm Sam Alexander, the mathematician and philosopher, and today I'm going to be reading Quadratic Forms Beyond Arithmetic by Alexander Merkurjev and Raman Parimala, which is published in the Notices of the AMS 2025. Introduction. The concept of quadratic forms can be traced back to ancient civilizations such as the Babylonians and Greeks. The Greeks, particularly Euclid in his famous work Elements, which I read when I was a kid, presented geometric methods for solving quadratic equations. The Greeks' focus on geometry and their methods continued to influence mathematicians for centuries. Rules for quadratic equations were also discussed in the 9 chapters on the mathematical art composed in China by 200 BC. The general formula for solving a quadratic equation in one variable, equivalent to the modern symbolic formula, was first stated by the Indian mathematician Brahmagupta in his treatise Brahmasphutta Siddhanta in 628 AD. A quadratic form over a commutative ring big R is a homogeneous polynomial sum aij xij of degree 2 in n variables x1 xn with coefficients aij in the commutative ring. In particular, the sum of squares x1 squared plus plus xn squared is a quadratic form defined over all commutative rings, because here the coefficients are 1, and 1 is always in the commutative ring, presumably. So note that they're implicitly assuming ring theory here where the rings have 1. The problem of representing integers as sums of squares dates back to ancient times. The Greeks, especially the Pythagoreans, were interested in the properties of numbers and their geometric interpretations. The concept of sums of squares is closely related to the Pythagorean theorem conceived in Mesopotamia 1800 BC, first stated precisely in the Shulba Sutra of Bodhayana 800 BC, and a statement of proof from China. In the 7th century, the Indian mathematician Brahmagupta considered what is now called Pell's equation, x squared minus ay squared equals 1, and found a method for its solution. Pell's equation, of course, in the 20th century saw a resurgence in importance due to its use in the proof of the DPRM theorem. One of the earliest and most significant results in the area of quadratic forms is Fermat's theorem on sums of two squares. In the 17th century, Fermat stated that an odd prime number p can be expressed as a sum of two squares if and only if p is congruent to 1 mod 4. Another milestone in the study of sums of squares is the four-square theorem proven by Lagrange in 1770. This theorem states that every positive integer can be represented as the sum of four squares, and that theorem is routinely taught in the first year of graduate algebra. Euler's sums of two squares identity, x1 squared plus x2 squared quantity times y1 squared plus y2 squared equals x1 squared y1 squared minus x2 sorry, let me start over. Euler's sums of two squares identity, x1 squared plus x2 squared quantity times y1 squared plus y2 squared equals x1 y1 minus x2 y2 quantity squared plus x1 y2 minus plus x1 y2 plus x2 y1 quantity squared, shows that the set of sums of two squares in a commutative ring is closed under multiplication. This statement was generalized to the binary quadratic form x squared plus ny squared by Brahmagupta. Brahmagupta, of course, lived long before Euler. Similar formulas also exist for the sums of 4 and 8 squares. In the beginning of the 19th century, Gauss completed the theory of composition of binary quadratic forms over the integers. Far-reaching generalizations in the 21st century are the higher composition laws of Bhargava, leading to asymptotics for the number of fields with bounded discriminant of degree at most 5. In the early 20th century, the main focus of the study of quadratic forms is the arithmetic theory over the rings of algebraic integers and number fields. Witt, in the 30s, laid the foundation of the algebraic theory of quadratic forms that deals with the study of quadratic forms over arbitrary fields. There was great progress in this study initiated by Pfister's theory of multiplicative forms in the 60s. Several open questions and conjectures were posed since then, a major one being the Milnor conjectures. Since the 80s, the introduction of powerful techniques from algebraic geometry transformed the study of quadratic forms, leading to great leaps like a solution of the Milnor conjecture. In this article, we trace the progress in the algebraic theory of quadratic forms over the last 4 decades. For simplicity, we only consider fields of characteristic different from 2, although the theory of quadratic forms in characteristic 2 is also well developed. We stay aside from the theory of quadratic forms over commutative rings, such as rings of algebraic integers, etc. In section 2, we briefly recall basic definitions. In the next section, we introduce a method of the study of quadratic forms in the last 4 decades based on the algebraic geometry. We introduce the quadric hypersurface, quadric xq associated with the quadratic form q, and a tool based on the study of closed subvarieties, algebraic cycles on the product of quadrics. In section 4, we state two theorems on the proof of Milnor conjectures that compare the graded Witt ring and the graded Motu-Galois cohomology via Milnor's K-theory of fields. Now, since the authors mentioned this as algebraic geometry, I'm going to be reading uppercase x as x and lowercase x as small x. In any other context, usually I'd read the uppercase x as big X and the lowercase x as x, but I find that in algebraic geometry, oftentimes the uppercase x's dominate. In the next section, some discrete invariants of fields, the U invariant and the Pythagoras number, that are defined by means of quadratic forms are considered. Although these invariants were defined a while ago, the newly developed techniques allowed us to obtain recent results in this direction. There are big open questions concerning these invariants. The determination of the U invariant of function fields of curves over a totally imaginary number of fields is the ultimate goal, while even the finiteness for rationals adjoin radical -1 remains open. Another big open question is the determination of the Pythagoras number of rational function fields over the field of real numbers, and the question is open even for reals adjoining 3 variables. Another discrete invariant, the dimension of a quadratic form, is discussed in section 6. One of the old intriguing questions on the determination of all possible splitting patterns of quadratic forms given dimension is still unsolved. In the last section, we introduced the Chow motives technique. Indecomposable direct summands of the motives of quadrics can be visualized in the diagrams defined in this section. Section 2, definitions. Basic references are 13 and 12. 13 and 2. Let big F be a field of characteristic not 2, that is 1 plus 1 is not 0 in big F. We write big F times for the multiplicative group of non-zero elements in big F. A quadratic form on a finite dimensional vector space big V over big F is a map Q, big V to big F, such that 1. Q of xv equals Q of small xv equals small x squared Q of V for all small x in big F and V in big V, and 2. The map BQ from big V cross big V to big F defined by the formula BQ of VV prime equals 1/2 Q of V plus V prime minus Q of V minus Q of V prime is a symmetric bilinear form. Note that the bilinear form BQ reconstructs Q by the equality Q of V equals BQ of VV. Thus, to give a quadratic form on a vector space big V is the same as to give a symmetric bilinear form on big V. The integer n equals the dimension of big V is called the dimension of the form Q. Let v1.vn be a basis for big V. If V equals some small xi vi, with small xi in big F as an arbitrary vector in big V, we have Q of V equals some ij aij xi xj, where aij equals aji equals bq of vi vj. Thus, Q is given by a quadratic homogeneous polynomial over big F. We say that Q is non-degenerate if the symmetric n by n matrix big A equals aij is non-degenerate. This is equivalent to the non-degeneracy of the bilinear form BQ. Below we'll consider non-degenerate quadratic forms only. The determinant of big A is well-defined modulo the subgroup big F times squared of squares in big F times. The discriminant of Q is -1 to the power n times n minus 1 quantity over 2, quantity times determinant of big A in big F times mod the square of big F times. Two quadratic forms Q big V to big F and Q prime big V prime to big F are isomorphic if there is a big F linear isomorphism F big V to big V prime such that Q of V equals Q prime of F of V for all V in big V. The forms Q and Q prime are isomorphic given only if they are given by the same quadratic polynomial in some bases for big V and big V prime. Let A1 dot A n be non-zero elements in big F. We write Langle A1 dot A n wrangle for the quadratic form some ai small xi squared on the space of n columns big V equals the nth power of big F. It is called the diagonal form, and it has a diagonal matrix in the standard basis for the nth power of big F. Every quadratic form over big F is isomorphic to a diagonal form A1 dot an for some not uniquely determined ai in big F times. If Q big V to big F is a quadratic form over big F and big L mod big F is a field extend and big L extending big F is a field extension, One can define a quadratic form Q big L on the big L space big L tensor over big F big V over big L with the associated bilinear form B on big L tensor over big F big V defined by B of small x tensor V, small x prime tensor V prime equals small x prime B Q of V V prime for all small x prime in big L and V V prime in big V. The orthogonal sum of two forms Q big V to big F and Q prime big V prime to big F is the quadratic form Q bot Q prime on big V O plus big V prime defined by Q bot Q prime quantity of V V prime equals Q of V plus Q prime of V prime. The form blackboard bold H equals 1 minus 1 is the hyperbolic plane. A quadratic form is hyperbolic if it is isomorphic to the orthogonal sum n times blackboard bold H, n times the hyperbolic plane of n bigger than 0 copies of the hyperbolic plane. A quadratic form Q big V to big F is called isotropic if there is a non-zero vector of V in big V such that Q of V equals 0, otherwise Q is called anisotropic. Every form Q is isomorphic to Q analytic bot K times the hyperbolic plane, where Q an is an anisotropic form and K beginning to get a 0. The integer W of Q equals K is called the Witt index of Q. It is equal to 0 if and only if Q is anisotropic. Two quadratic forms Q and Q prime are Witt equivalent if the forms Q anisotropic and Q prime anisotropic are isomorphic. The set Witt of big F of equivalence classes of quadratic forms over big F is the Witt ring of big F with respect to the orthogonal sum and tensor product of forms. For example, Witt ring of the reals is isomorphic to the integers, and integer n bigger than 0 corresponds to the form n1 under the isomorphism. One of the most important properties of the Witt ring: two quadratic forms Q and Q prime are isomorphic if and only if Q equals Q prime in the Witt ring of big F and dimension of Q equals dimension of Q prime. The ideal of big F of even dimensionless forms in the Witt ring of big F is called the fundamental ideal. The quotient Witt ring of big F mod the ideal of big F is isomorphic to integers mod 2. The powers nth power of big I of big F of the fundamental ideal form a filtration on the Witt ring of F, on the Witt ring of big F. The discriminant yields an isomorphism between the ideal of big F mod the square of the ideal of big F and big F times mod the square of big F times. The determination of all the quotients nth power of the ideal of big F mod n plus 1th power of the ideal of big F is one of the fundamental problems of the algebraic theory of quadratic forms. See section 4 below. Let a1 an in big F times the 2 to the n dimensional quadratic form double angle a1 an double wrangle equals 1 minus a1 tensor 1 minus a2 tensor tensor 1 minus an is called the n-fold Pfister form. The nth power of the ideal of big F of the fundamental ideal in the Witt ring is generated by the n-fold Pfister forms as an abelian group. An n-fold Pfister form is either anisotropic or hyperbolic. Example: let big K equals big F adjoint fractions of a to the 1/2 be a quadratic field extension of big F. The norm form Q big K to big F defined by Q of small x plus small y a to the 1/2 equals small x squared minus a small y squared is the one-fold Pfister form double angle a double wrangle. Let a be non-zero elements of big F and let big Q be a quaternion four-dimensional associative non-commutative big F algebra with basis 1 I j k and multiplication table I squared equals a, j squared equals b, and k equals ij equals minus ji. The reduced norm form Q to big F defined by Q of small x plus small y I plus small z j plus t k equals small x squared minus a small y squared minus b small z squared plus a b t squared is the two-fold Pfister form double angle a b double wrangle. For a triple of elements a, b, c, non-zero elements of big F, there is an octonion, non-associative, non-commutative, 8-dimensional algebra big C that admits a norm quadratic form Q big C to big F that is the three-fold Pfister form double angle ABC double wrangle. Note that norm forms Q in all the examples are multiplicative, i.e. the product of two values of Q is a value of Q. By the Hurwitz theorem, There are no algebras of dimensions not 1, 2, 4, and 8 with a multiplicative norm. Nevertheless, the set of non-zero values of an n-fold Pfister form is closed under multiplication for every n. In particular, the sum of 2 to the n squares is a multiplicative quadratic form over any field. Now, this has already gone totally over my head, but I'm going to continue reading it anyway. Algebrogeometric methods. During the last 3 decades, the methods of algebraic geometry interfaced algebraic theory of quadratic forms. One can associate to every quadratic form Q big V to big F over big F the quadratic hypersurface XQ, simply called the quadric of Q, given by the equation Q of V equals 0 in the projective space of big V. The quadric XQ has dimension of Q minus 2, and it is smooth if Q is non-degenerate. The variety XQ is integral if the dimension of Q bigger than or equal to 3. By definition, XQ has a point over big F if and only if the form Q is isotropic. More generally, XQ has a point over a field extension, big L extending big F, if and only if Q is isotropic over big L. For example, the quadric XQ prime, where Q equals small x squared plus small y squared plus small z squared, has no points over the reals, but it has points over the complex field. The two quadrics, XQ and XH, are isomorphic if and only if the quadric forms Q and H are similar, that is, each of the forms Q and H is a big F multiple of the other. We write big F of Q for the function field big F of XQ. Note that Q is isotropic over big F of Q. Indeed, if small x1 dot 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 small xn are homogeneous coordinates in the projective space of big V, we can view the rational functions small xi over small x1 as the elements in the multiplicative group of big F rationally adjoint Q, satisfying Q of 1, comma, small x2 over small x1 dot dot dot, comma, small xn over small x1 equals 0 in big F of Q. Thus, the equation Q of V equals 0 has non-zero solution over the field big F of Q. The field big F of Q is a general splitting field of Q. The form Q is isotropic over the field extension big L, field extending big F, if and only if there is a big F place from big F of Q to big L, that is a big F algebra homomorphism of evaluation big F subalgebra big R subset big F of Q to big L. Consider the following example of an application of the theory of algebraic cycles. Let Q be an anisotropic quadratic form over big F and let big L extending big F be a field extension. We would like to know when Q is isotropic over big L, i.e. the equation Q of V equals 0 has non-zero solution over big L. Typically, the extension big L extending big F is finitely generated, so we can choose an integral variety y over big F such that big L is isomorphic to the function field of y over big F. By the main property of the quadric, XQ has a point over big L equals the function field of y over big F, if and only if there is a morphism from spec big L to y, or equivalently a rational morphism y to XQ defined on a non-empty open subset big U subset y. The closure of the graph of big U injecting into XQ in the product y times XQ yields a cycle class of dimension d equals dimension of y in the Chow group sub d of y cross XQ of rational equivalence classes of cycles of dimension d on y cross XQ. Conversely, a prime algebraic cycle on y cross XQ of dimension d that is birational when projecting to y yields a rational morphism y to XQ and therefore a point of XQ over big L. Thus, one can use the machinery of algebraic cycles. In particular, one can obtain new cycles by intersecting with other cycles, for example, with the Chern classes of the vector bundle, such as the tangent bundle, by considering pullbacks and pushforwards with respect to certain morphisms, and also applying the Steenrod operations modulo 2. Milnor conjectures. The most spectacular achievement in the algebraic theory of quadratic forms is the solution of the Milnor conjectures. Now, this is totally over my head, but I do know that these Milnor conjectures are a very big deal and have been talked about quite a bit in the 21st century. The Milnor big K theory, big K, big M star of big F, of a field big F, is the graded quotient ring of the tensor integers algebra of the multiplicative group big F times by the ideal generated by the tensors A tensor B, where A, B in the multiplicative group of big F with A plus B equals 1. In particular, big K big M 0 of big F is the integers, and big K big M 1 of big F is the multiplicative group of big F. The group big M, the group of big K big M n of big F is generated by the symbols A1 dot dot an, where AI in the multiplicative group of big F, that are multiplicative with respect to every variable when the other variables are fixed, and satisfy the Steinberg relation, a1 dot 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 an equals 0 if ai plus aj equals 1 for some I not equal to j. I don't know what these curly braces indicate here. Obviously not sets. The assignment mapping curly left brace a1 dot 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 an curly right brace to double Langle a1 dot 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 an double Langle yields a well-defined graded ring homomorphism S big F from big K big M star of big F to ideal star of big F mod ideal star plus 1 of big F. I don't know what that star there means in the superscript above the big I. Let big gamma big F be the absolute Galois group of a field big F, i.e. big gamma big F is the Galois group of a separable closure of big F over big F. We write big H star of big F for the graded cohomology ring of big gamma big F with coefficients in integers mod 2. The multiplication in big H star of big F is given by the cup product, cup. In particular, big H0 of big F is integers mod 2, and big H1 of big F is multiplicative group of big F mod the square of the multiplicative group of big F. For every A in the multiplicative group of big F, write parens A for the corresponding cohomology class in big H1 of big F. The assignment left curly brace A1 dot 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 A and right curly brace maps to corresponding cohomology class of A1, cup corresponding homology class of A2, cup dot 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 cup corresponding homology class of AN, yields a well-defined graded ring homomorphism H big F from K big M star of big F to big H star of big F called the norm residue homomorphism mod 2. Thus we have the following diagram of graded ring homomorphisms. Big K big M star of big F mod 2 big K big M star of big F maps via S big F to ideal star of big F mod ideal star plus 1 of big F, and also maps via H big F to big H star of big F. Milnor has conjectured in the 70s that both maps S big F and H big F are isomorphisms for all fields. This conjecture for n equals 2 was settled by the first author in the 80s, leading to a solution of the long-standing question on the generation of the two torsion of the Brouwer group of a field by quaternion algebras. Blavatsky, in reference 24, proved one of the Milnor conjectures. Theorem. The graded ring homomorphism H big F is always an isomorphism. In the proof, Blavatsky introduces a number of revolutionary ideas and tools. The main tool is the motivic cohomology defined by Blavatsky. Another tool is the motivic-Steenrod operations defined by Blavatsky in analogy with the classical topological operations. The motivic analogues of some of the basic operations, the Milnor operations, played an essential role in the proof. Enriching Blavatsky's methods, Orlov, Vishik, and Blavatsky proved in reference 16 another Milnor conjecture. Theorem. The graded ring homomorphism S big F is always an isomorphism. In particular, for every n bigger than or equal to 0, we get a group isomorphism. Cn big F equals Hn big F compose the inverse of Sn big F from the nth power of the ideal of big F mod the n plus 1th power of the ideal of big F to big H to the n big F. We can call the maps Cn big F the cohomological invariants of quadratic forms. These invariants determine anisotropic quadratic forms up to isomorphism as follows. Suppose we are given two anisotropic quadratic forms f and g, and we want to decide whether f and g are isomorphic or equivalently that the form q equals f bot minus g is hyperbolic. We compute the cohomological variance Cn big F of q one by one starting with n equals 0. Note that the next invariant is defined if the previous one vanishes. The invariant C0 big F takes q to its dimension mod 2 in integers mod 2 equals big H0 big F. If this invariant vanishes, i.e. q has even dimension, then q is in the ideal of big F. The invariant C1 big F of q is equal to the discriminant of q in the multiplicative group of big F mod the square of the multiplicative group of big F equals big H1 of big F. If the discriminant of q is trivial, the form q belongs to the square of the ideal of big F, and we can compute C2 big F of q. This is the class of the Clifford algebra of q in the subgroup BR of big F bracket 2 equals big H2 of big F of the Brouwer group. BR stands for Brouwer. This is the class of the Clifford algebra of q in the subgroup Brouwer subgroup of big F bracket 2 equals big H2 of big F of the Brouwer group of classes of exponent 2. If this vanishes, then q is in ideal third of big F, and so on. If Cn of big F of q equals 0, i.e. q in the ideal n plus 1 of big F, and dimension of q less 2 to the n plus 1, then q is hyperbolic, and the forms f and g are isomorphic. Field invariance. We discussed two integer invariants of fields associated with quadratic forms, namely the U invariant and the Pythagoras numbers. U invariant. The U invariant, U of BF of a field BF, is the largest dimension of an anisotropic quadratic form over BF. For example, the U invariant of the reals is infinity, and the U invariant of the complex field is 1. The U invariant of a finite field is 2. The U invariant of a local field is equal to 4. The Hasse-Minkowski theorem implies that the U invariant of a totally imaginary number field is 4. The formula U invariant of the ring of formal power series over big F in variable t equals 2 times the U invariant of big F shows that every power of 2 is the U invariant of some field. Breaking the myth that all invariants of fields associated with quadratic forms are a power of 2, it was shown in reference 15 that every even integer is the U invariant of some field. On the other hand, it is known that the U invariant is not equal to 3, 5, or 7. It is expected that every odd integer bigger than or equal to 9 is the value of the U invariant. Ishbolden has shown in reference 7 that there are fields of U invariant 9. In reference 22, Vishek proved that every integer of the form 2 to the m plus 1 form bigger than or equal to 3 can be the U invariant of a field. The behavior of the U invariant of finite field extensions has been studied extensively. We have the following theorem of Leap for finite field extensions. Theorem. Let big L extending big F be an extension of degree n, then the U invariant of big L is less than or equal to n plus 1 quantity over 2 times the U invariant of big F. There may be bounds for the U invariants of finite extensions independent of the degrees of the extensions. The behavior of the U invariant under rational function field extensions is not well understood. Question: if the U invariant of big F is less than infinity, is the U invariant of big F with variable t rationally added less than infinity? If this question has an affirmative answer, then it follows that there are bounds independent of the degree for the U invariant of finite field extensions. In fact, the above question is wide open if big F is a totally imaginary number field. Even for the function fields of p-adic curves, the question remained open until the late 90s when the first finiteness results emerged from Merkurjev and Hoffman-van Giel. A theorem of Saltman on bounding indices of elements in the two torsion of the Brouwer group was pivotal to this theorem. We have the following theorem for function fields of p-adic curves. Theorem. Let big K be a p-adic field and big F the function field of a curve over big K, then the U invariant of big F is 8. We have the following more general extension of the above theorem, which fundamentally uses a theorem of Heath-Brown on the zeros of systems of p-adic quadratic forms. Theorem. Let big K be a p-adic field and big F the function field of a variety of dimension d over big K, then the U invariant of big F is 2 to the d plus 2. We also have the following theorem extending to general complete discretely valued fields, which uses the patching techniques of Harbider, Hartmann, Krashen. Theorem. Let big K be a complete discretely valued field with residue field kappa. Let big F be the function field of a curve over big K. Suppose that the characteristic of kappa is not 2, and there exists an integer d such that the U invariant of big L is less than or equal to n for all finitely generated extensions of kappa of transcendence degree at most 1. Then the U invariant of big F is less than or equal to 2n. Pythagoras number. The Pythagoras number P of big F, Pythagoras number of big F, of a field big F, is the smallest integer n such that every sum of squares in big F is the sum of at most n squares in big F. For example, the Pythagoras number of the reals equals the Pythagoras number of the complex field equals 1. If big F is a real number field, then 3 is less than or equal to the Pythagoras number of big F is less than or equal to 4. The study of the Pythagoras number of fields which are formally real, i.e. minus 1 is not a sum of squares in the field, is interesting. The following theorem answers a question of Pfister. Theorem. Every positive integer n bigger than or equal to 1 is the Pythagoras number of a formally real field. The determination of Pythagoras numbers of rational function fields reals rationally adjoin small x1 small xn has a long history. Pfister theory leads to Pythagoras number of reals rationally adjoin small x1 small xn less than or equal to 2 to the n. We have Pythagoras number of reals rationally adjoin small x equals 2, and Pythagoras number of reals rationally adjoin small x1 small x2 equals 4. We have bounds n plus 2 less than or equal to the Pythagoras number of reals rationally adjoin small x1 small xn less than or equal to 2 to the n. One has the following sharper bound for the Pythagoras number of big F if big F is a formally real field of transcendence degree d over a subfield, namely Pythagoras number of big F bigger than or equal to d plus 1. A major open question in this area is the following. What is the Pythagoras number of reals rationally adjoin small x1, small x2, small x3? More on the arithmetic side, interesting questions arise concerning the Pythagoras number of a formally real function field over the field of rational numbers. The inequality Pythagoras' number of rationals rationally adjoining small x less than or equal to 8 goes back to Landau, 1906. And we have the Pythagoras number of the residue field of small x equals the Pythagoras number of k plus 1 less than or equal to 5 for real number of fields k. That's rather the Pythagoras number of k rationally adjoining small x equals Pythagoras number of k plus 1 less than or equal to 5 for real number of fields k. Conjecturally, for a function field big F in one variable over a number field, Pythagoras number of big F is less than or equal to 5. The estimate Pythagoras number of big F less than or equal to 7 is due to Colliot-Telaine, and a sharper estimate Pythagoras number of big F less than or equal to 6 is due to Pop. One has the following general result for a function field big F in d variables over a number field, namely Pythagoras number of big F less than or equal to 2 to the d plus 1. This combines the Milnor conjecture and a global local principle for the Galois cohomology of higher dimensional function fields due to Janssen in reference 8. Dimensions of quadratic forms. In this section, we discuss results on the dimension of quadratic forms satisfying certain conditions. Possible dimensions of anisotropic quadratic forms in the nth power of the ideal of big F. An anisotropic n-fold Pfister form over big F belongs to the nth ideal of big F and has dimension 2 to the n. By an Arison-Pfister theorem, every non-zero anisotropic form in the nth power of the ideal of big F is of dimension at least 2 to the n. Are there other restrictions on the dimensions of anisotropic quadratic forms in the nth power of the ideal of big F? Karpenko proved in reference 11 the following general result. Theorem. Let Q be an anisotropic quadratic form such that Q is in the nth power of the ideal of big F for some n bigger than or equal to 1. If the dimension of Q is less than 2 to the n plus 1, then the dimension of Q equals 2 to the n plus 1 minus 2 to the I plus 1 for some I between 0 and n inclusive. All other even degrees at least 2 to the n plus 1 are possible. For example, the possible dimensions of anisotropic quadratic forms in the fourth power of the ideal of big F are 0, 16, 24, 28, 30, 32, 34, 36, ... Hoffman's separation theorem. Let Q and H be two anisotropic quadratic forms over big F. When is Q isotropic over the field big F rationally adjoin H? Equivalently, is there a rational morphism xh to xq? If Q is hyperbolic over big F rationally adjoin H, then the dimension of Q bigger than or equal to the dimension of H. This inequality does not hold in general if Q is just isotropic over big F rationally adjoin H. Example. Let H be a general n-fold Pfister form, i.e. H is similar to an n-fold Pfister form, and Q a subform of H of dimension bigger than 1/2 dimension of H. Over the field big F rationally adjoin H, the Pfister form H is isotropic and hence hyperbolic. Therefore, Q is isotropic over big F rationally adjoin H. Note that the numbers dimension of Q and dimension of H in the example are not separated by power of 2. The following result proved by Hoffman in reference 5, known as the separation theorem, explains this observation. Theorem. Let Q and H be two anisotropic quadratic forms over big F. Suppose the dimension of Q less than or equal to 2 to the n less the dimension of H for some n bigger than or equal to 0. Then Q is anisotropic over big F rationally adjoin H. The first Witt index. Let Q be an anisotropic quadratic form of dimension at least 2 over big F. The form Q sub big F rationally adjoin Q is anisotropic. I'm not sure what this big F of Q is, whether that's big F rationally adjoin Q or what. Its Witt index is then positive, denoted I1 of Q, and is called the first Witt index of Q. The typical value of the first Witt index is equal to 1. If Q is a generic form, e.g. Q equals small x1 ... small xn over the field big F rationally adjoin small x1 ... small xn of rational functions, then the first Witt index of Q is 1. On the other hand, if Q is an anisotropic m-fold Pfister form, then the first Witt index of Q is 2 to the n minus 1, since Q is hyperbolic over big F rationally adjoin Q. All possible values of the first Witt index of all quadratic forms of given dimension n were determined by Karpenko in reference 9. Theorem. Let Q be an anisotropic quadratic form of dimension n, write n minus 1 in base 2, n minus 1 equals 2 to the k1 plus ... plus 2 to the kr, with 0 less than or equal to k1 less k2 less kr. Then the first Witt index of Q minus 1 equals 2 to the k1 plus ... plus 2 to the ks for some s equals 0, 1 ... or r minus 1. In other words, the first Witt index of phi minus 1 is the remainder upon dividing dimension of q minus 1 by some power of 2 less than the dimension of q. In fact, all values of the first weight index of q given in the theorem are attained by some forms over appropriate fields. In particular, the number of possible values of the first weight index of q is equal to the number of ones in the base 2 expression of the integer dimension of q minus 1. Oh, that's interesting. It's not every day that you see bases occur in this type of mathematics. Example, if dimension of q equals 2 to the m plus 1, then the first weight index of q equals 1. This can also be deduced from Hoffman's separation theorem. All possible values of the first weight index of an anisotropic form of dimension 2 to the m are the 2 powers 1, 2, 2 squared, 2 to the m minus 1. The largest 2 to the m minus 1 is the first weight index of an m-fold Pfister form. Splitting patterns of quadratic forms. Let q be a quadratic form of dimension n over big F, and let I0 less less IH minus 1 less IH equals, I assume that's the greatest integer, not bigger than, I assume that's floor function of n over 2. Denote all weight indices of quadratic forms q big L over all field extensions big L of big F. The tuple splitting pattern of q equals I0 I1 IH minus 1 IH of strictly increasing integers is called the splitting pattern of q. The smallest integer I0 is the weight index of q. If q is anisotropic, i.e. I0 equals 0, the integer I1 is the first weight index of q. All possible splitting patterns of quadratic forms of small dimension are determined by Vishik in reference 21. For example, the splitting patterns of anisotropic 9-dimensional forms are 0, 1, 4 and 0, 1, 2, 3, 4. For arbitrary n, it is unknown which splitting patterns of n-dimensional forms occur. Example, excellent form. We employ the following inductive definition. An anisotropic quadratic form q of dimension n is called excellent if either q equals 0 or there is an excellent form q prime such that the dimension of q prime less the dimension of q and q but q prime is a general Pfister form. Quadratic forms of dimension up to 3 are excellent. A form of dimension 4 is excellent if and only if it has trivial discriminant. The splitting pattern of an excellent form is determined inductively as follows. If in the definition the dimension of q plus the dimension of q prime equals 2 to the m, then the splitting pattern of q equals singleton 0 union splitting pattern of q prime plus n minus 2 to the m minus 1. In particular, the splitting pattern of an excellent form q depends just on the dimension of q. For example, if q is an excellent form of dimension 25, then the splitting pattern of q equals 0, 9, 12. Ishbolden dimension. Let q be a quadratic form over big F. Ishbolden defined an integer associated with the quadratic xq prime called the Ishbolden dimension. The Ishbolden dimension of xq equals the dimension of xq minus the first weight index of q plus 1 equals the dimension of q minus the first weight index of q minus 1. Example. Let h and q be as above, as in example 6.2, which was way above. So h is a general n-fold Pfister form, i.e. h is similar to an n-fold Pfister form, and q is a subform of h of dimension bigger than 1/2 dimension of h. Then the Ishbolden dimension of xh equals the Ishbolden dimension of xq equals 2 to the n minus 1 minus 1. Note that q is isotropic over the big F rationally adjoint h, and h is isotropic over big F rationally adjoint q. Theorem. Let q be a quadratic form and let y be a complete possibly singular algebraic variety over big F with all closed points of even degree and such that y has a closed point of odd degree over big F rationally adjoint q. This holds, for example, if y has a point over big F rationally adjoint q. Then the Ishbolden dimension of xq is less than or equal to the dimension of y, and in the case that the Ishbolden dimension of xq equals the dimension of y, the form q is isotropic over the function field of y over big F. The following corollary can be viewed as a variant of the separation theorem. Corollary. Let h and q be anisotropic quadratic forms. If h is isotropic over big F rationally adjoint q, then the Ishbolden dimension of xq is less than or equal to the Ishbolden dimension of xh, and in the case that the Ishbolden dimension of xq equals the Ishbolden dimension of xh, the form q is isotropic over big F rationally adjoint h. Chow motives of quadrics. The constructions and results in this section are due to Vishik. There is a functor from the category of smooth projective varieties to the additive category of Chow motives, taking a variety x to its motive of x, and a morphism f x to y of varieties to the class of the graph of f in the Chow group of the classes of algebraic cycles in x cross y. I do not know what Chow motives are, so this is all totally nonsense to me. The motive of the projective n space, decomposes into a direct sum, integers, direct sum, integers, Tate motive 1, direct sum, direct sum, integers, Tate motive n. Here, integers, left parentheses, I, right parentheses, are the Tate motives, so I pronounce that as the integers Tate motive I. I have no idea what a Tate motive is. Let X be a quadratic of dimension n over an algebraically closed field, then the motive of X is isomorphic to integers, direct sum, Tate motive, integers 1, direct sum, direct sum, integers, Tate motive n equals the motive of projective n space if n is odd. And the motive of X is isomorphic to integers, direct sum, integers, Tate motive 1, direct sum, direct sum, integers, Tate motive k minus 1, direct sum, integers, Tate motive k, direct sum, integers, Tate motive k, direct sum, integers, Tate motive k plus 1, direct sum, direct sum, integers, Tate motive n if n equals to k. Note that the motive integers, Tate motive k appears in the decomposition twice if n equals to k. We introduce the set of symbols big lambda of x equals big lambda of n equals the set 0, 1, k, k bar, 1 bar, 0 bar, where k equals floor function of n over 2, and a bijection between big lambda of x and the set of Tate motives in the decomposition of the motive of x as follows. I is bijectively mapped to integers Tate motive of I, and I bar is bijectively mapped to integers Tate motive n minus I for I equals 0, k. Over an arbitrary field, the motive of x is a direct sum big M1 direct sum big MS of indecomposable motives. The collection of indecomposable motives, big Mi, in the direct sum is unique up to isomorphism. Over an algebraic closure of big F, every motive big Mi is the sum of certain Tate motives. Thus, the set big lambda of X is the disjoint union of S subsets big lambda 1 big lambda S, so that for every I, the elements of big lambda I correspond to the Tate motives in the decomposition of big Mi over an algebraic closure. The motive of X is indecomposable if and only if S equals 1. We'll consider the diagrams, graphs, with vertices given by the set big lambda of X. A connection is an edge in the diagram such that both ends at the edge belong to the same subset big lambda I, but we don't necessarily connect every two vertices in the same subset big lambda I. We'll draw vertices horizontally in the order they appear in the definition of big lambda of X, with one exception. If n is even, we draw the vertices k and k bar one under the other to indicate that they correspond to the same Tate motive, integers Tate motive k. Below are the diagrams for 6-dimensional hyperbolic, respectively 7-dimensional generic quadrics. We have some diagrams. Example: let Q be a subform of dimension 2 to the m minus 1 plus 1 of a general anisotropic m-fold Pfister form H. Rost proved that there is a direct sum and big M of the motive of xq such that over an algebraic closure big M is isomorphic to integers direct sum integers Tate motive 2 to the m minus 1 minus 1. This motive depends on H only, not on the choice of Q. It is called the Rost motive of H and denoted big M H. So big M H is Rost motive of H. The motive of the Pfister quadric, the motive of XH, is isomorphic to the Rost motive, direct sum, Rost motive, Tate motive 1, direct sum, direct sum, Rost motive, Tate motive 2 to the m minus 1 minus 1. For example, if m equals 3, the diagram of the motive of XH looks as follows, and we have a pretty diagram with 1, 2, 3, 4, 5, 6, 7, 8 points. Example: let Q be an excellent quadratic form of dimension bigger than -2. The motive of XQ is a direct sum of twists of Rost motives of the general Pfister forms appearing in the definition of an excellent form. For example, the diagram of the motive of the 11-dimensional excellent form double Langle ABC double wrangle but D Langle AB minus AB wrangle is as follows. And it's a pretty diagram with a bunch of dots. The shape of the diagram depends only on the dimension of Q. All connections in the diagram for an excellent form are called the excellent connections. Let Q be an anisotropic form with a splitting pattern I0 equals 0, I1 IH minus 1, IH, and x equals xq prime, n equals dimension of x. There are the following standard connections in the diagram of X. Proposition: that ij equals 0, 1 floor of n over 2 would be such that ir minus 1 less than or equal to ij less ir prime, where 1 less than or equal to r less than or equal to h, and I plus j equals ir minus 1 plus ir minus 1. Then the symbols I and j bar are connected in the diagram of X. The standard connections for an excellent form coincide with excellent connections. Vishek proved, in reference 23, that for an arbitrary form, excellent connections also appear in the diagram. Theorem. Let Q be an anisotropic quadratic form of dimension at least 2, and let F be an excellent form of the same dimension. Identify canonically big lambda of xq and big lambda of xf. If two symbols are connected in big lambda of xf, then they are also connected in big lambda of xq. The theorem shows that the diagram of xf is contained in the diagram of xq. In particular, the diagram of an excellent form contains the smallest number of connections among the diagram of forms of the same dimension. Example, let Q be an anisotropic Albert form, i.e. Q is a 6-dimensional quadratic form with trivial discriminant. Its splitting pattern is 0, 1, 3. Below are the two diagrams with the standard and excellent connections respectively. Combining these diagrams, we see that all vertices are connected, hence the motive of xq is indecomposable. Indecomposability of the motive of a quadratic is used in the following application due to Ishbolden and Karpenko, in reference 12. Theorem. Let Q and H be two anisotropic quadratic forms of the same odd dimension. Suppose that Q is isotropic over big F rationally adjoint H and H is isotropic over big F rationally adjoint Q. In addition, if at least one of the two motives, the motive of xq and the motive of xh, is indecomposable, then the forms Q and H are similar. And that's the end. Acknowledgements. We're grateful to Nikita Karpenko, Alexander Vishek, and Vanapali Suresh for the useful comments. We thank Manjul Bhargava for pointing out to us the contributions from ancient civilizations. Interesting paper. Reading this has given me a very interesting mental subjective feeling. I did not understand much of the paper, but I think that I will gain a lot of insight from my subconscious mind digesting this paper